Hello, differential equation students. So in this section, we're going to continue to solve continue to solve first order linear differential equations. And we looked at last time how do we solve both the homogeneous and the non-homogeneous. One thing that I want to show you is how do we we use the indefinite integral, but I want to show you how do you work with definite integral. So the only changes that we're going to make here, only difference that we're going to make here is how do we change these things, right? So how do we change these things? So let me quickly go through the theory in here, and then I'll try to implement that using the problem that we have, right? So let's take a look. Let me copy paste it here. So here's the integration is both sides. The only thing we are changing here is, as I said, from going from indefinite to definite integral, right? So we are no longer going to have empty, 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 empty in here, but now we're going to have some sort of an integrating both sides. I'm going to say, from 0 to x, right? So in this case, let's just say 0 to x, assuming that the interval of is 0 to infinity. That means x could be any number. We're trying to solve the solution, right? The solution is we want it to be well defined for the entire positive real line. Let's just say from 0 to x. It does not have to be 0 to x. It could be any initial value. It could be 1 to x, it could be 2 to x, it could be 3 to x, and so on. So it doesn't matter. For example, in this particular problem, that we did over here, 0 might not be even, the differential equation is not even well defined for 0. So you have to be careful there. So 0 might not work. So the initial condition for this is going to be, if at all it is, it has to be something with the y of 1 equals something, right? So 0 might not work. So therefore, although we kind of looked at it here previously, the 0 might not be a good idea for this one as a solution. Maybe, we should go with the y of 1 is equal to 1. Y of 0 equal to 1 might not be a good idea there. So then that's what I did, but I think somehow I plugged in 0 there. So y of 1 is equal to 1, not y of 0 is equal to 1. And then, we can solve that. So it should be y of 1 is equal to 1, right? Because that's what I plugged in here. I plugged in 1 and 1 over there for x. Anyways, so going back to what I was saying is that, so we need to be careful. So in general, we can say in this particular case, it's no problem. So we can go with the 0 to infinity, but again, it depends on the problem. You may have to go with the 1, 2, or -1, -5, and so on. Depends on whether the differential equation, the solutions are well defined in the particular interval or not. So in this case, for the sake of simplicity, let's go with from 0 to x. So then what's going to happen is that my lower limit here is going to be changed, and then upper limit is going to here change. So the way that it's going to change is the following. I'm going to have something like this. So I'm going to say this is going to be from 0 to x, and this also going to go from 0 to x, and this also going to go from 0 to x, and this is also going to go from 0 to x, and so on. But then we have an issue there. What is the issue? The issue here is well, this is 0 to x, so you can, it's a very, it's a bad notation to have a 0 to integrating with respect to x and then plugging in x. It's going to be really not so good. It's going to confuse and so on. For that reason, that's a dummy variable, so we can always change it. We are going to change it to s. But then this is going, so this is then going to be s. Since it's an x, again, we don't want x here. We want something else. We already used s, so we have to use something else. I'm going to go with the z, right? So so you have to be careful with that variable, dummy variables when we work with them. So this is going to be z. I'm going to call this as s. I'm going to call this as s, and I'm going to call this as s, right? And so on. So it works out okay. And again, one other thing, whenever we say y, this y is not just y is a function of x, right? So generally speaking, this is a y as a function of x, but again, here is integrating with respect to s. So therefore, I'm going to say this y as a function of s, right? So these are some, some subtle things that when you go from definite indefinite integral to definite integral, that you have to be careful. And so therefore, what's going to happen? So this step right here is going to be, is going to have a lot of changes. It's going to have a lot of changes. So how are those changes are going to be? So what's going to happen is that, so let me go through the process. What's going to happen in the process? So let's take a look at, the process that we had earlier and how these things are going to change in that process. So here's the process that we followed last time. And here's the process that we followed last time. So let me copy paste it. let me show you what are the things that are going to change in that process. So first of all, p of x, now this is going to be from p of s ds and 0 to x. That's number one, right? And then this is going to be, y of s. Actually, this step is going to change a whole lot, right? That step is going to change a whole lot. So let me just show that how that step is going to change. Let me delete all this. We don't need that. All right. So then what I'm going to have now, I have this step, right? That's what's going to give you the other steps. So now let me show you how that I'm going to be replacing it over here. So the step 4, the change is going to be, again, the changes are all in the purple, right? The blue one is already there. The changes are all in purples. So here I'm going to have, when I integrate this, this is going to give me, again, antiderivative derivative by the fundamental theorem of calculus. That is going to be y of s e to the 0 to s p of z dz, and then the lower limit is 0, and then the upper limit is x, and then equals that same thing over here, right? That's not going to change. So 0 to x e to the 0 to s p of z dz, and then q of s ds, and then this step, just this step, is going to change a little bit, and that would be, now I plug in the upper limit. This is going to be y of x function e to the integral of 0 to x, and then the p of z dz, minus, if I apply the lower limit, right? If I apply the lower limit, let me change the color to some other color. Let me change it to a green. So then I have y of 0, then I have e to the 0 to 0 p of z dz. But again, I have the integral is from 0 to 0. That's simply a 0. So the whole thing is going to be 0. Since the whole thing is going to be 0, that's going to go away, right? That's going to go away, and that's going to be simply 0. Since that is 0 and e to the 0 is equal to 1, right? So then this is going to go away. This is going to go away, and it's going to simply become 1, right? So I'm going to even let that go. So that's what I put in a green. It's much easier. Then whatever that I have right here, I have to work with the integral, and then we're going to solve it. So let me show you how do I implement this in the next problem. But here's the general idea in working out the details, right? So what you're going to have is, rather than this step that you had previously, now you're going to have this, rather than having a simple step previously. Now you're going to be, that is going to be replaced by this. So we don't need this. I can delete this one. So the next step, as I showed you how it is, right? So we don't need that. Now that previous step is now replaced by this, and then you're going to, the next step as, you're going to solve for y of x. I'm going to solve for y of x, and that's the steps in here. So let me show you how to implement this in the problem that I have as an example. Let's take a look. How do we execute that? All right. I think I can do it. Let's see. Step number 1, no problem. Standard form is already there, so that's good to go. No big deal, right? It's already in the standard form. I don't have to worry about it. Step 2 is identifying p of x and q of x. So in this case, I should say p of x and q of x. Q of x, which is p of x is -3, and the q of x is +6. The next step is, step 3 is now integrating factor. This is a little bit interesting. It's not a big deal. It's not going to change much in here. And the factor is going to be e to the integral of p of x. I'm going to say p of, what did we say here? P of s, or I'm going to say p of z dz, and then 0 to x. And that would be e to the integral of 0 to x minus 3 dz. If I do that, I'm going to have e to the if I do the integration, that's going to give me e to the negative 3z 0 to x. If you simplify that, that is going to be e to the negative 3x minus 0, which is e to the negative 3x, right? That's all I have there. And the step 4 is little crazy. A little, for step 4 it's not a big deal. It's really not, very hard one, but you have to be really, really careful. So then this is going to be, and I'm going to, show you this step itself. I'm going to show you from there itself so that you know what I'm doing. So this is going to be, y if you remember the previous step that I had right here, which I erased it. If you remember the previous step, if you go back to the video and see it, right, this is what I had, which is yfs, e to the what were the integrating factors? So it's going to be e to the 3s, e to the 3s, and then 0 to x equals integral of 0 to x, and this is, e to the negative 3s times q, which is 6, and ds, which would be, by the way, if I simplify that, let me plug in the upper and lower limit. When I plug in the upper limit, this is going to be y of x e to the negative 3x minus y of 0, just like you see them right here, right? Y of 0 equals, now if I integrate this, this is going to be e to the negative 3s divided by negative 3 times 6. The lower limit is 0, the upper limit is x. And if I simplify this, this is going to be negative 2 e to the negative 3s. The lower limit is 0, the upper limit is x. Here I'm going to have on my right hand side, I have y of x, e to the negative 3x. And the initial condition is given to me. So therefore, I'm going to say this is equal to 1, right? That is the beauty with this one. And, if I simplify this, and I'm going to have, y of x, e to the negative 3x minus 1 equals, when I plug in the upper limit, this is going to be negative 2 e to the negative 3x. When I plug in the lower limit, this is going to be negative e to the 0, which is 1. So if I simplify this, this is going to be negative 2 e to the negative 3x, and this is 1 anyway, so this whole thing is going to be plus 2. So therefore, my y of x e to the negative 3x is going to be negative 2 e to the negative 3x. 2 plus 1 is going to be 3. And therefore, the solution is going to be y of x equals, I'm going to divide both sides by e to the 3x. So if I divide both sides by e to the negative 3x, I'm going to have negative 2 e to the negative 2. That's going to be gone. And plus 3 e to the 3x. And if I rewrite it, the solution I'm going to say would be y of x equals 3 e to the 3x minus 2. And that's how we solve using definite integral. And why is it important? This looks like a little bit more steps. Why is it important? Why do you want to do it? Especially if you have to deal with some functions that are, piecewise functions. You're going to see some problems on the worksheets, right? You're going to see some problems where this q of x, right, happens to be some sort of a piecewise function. 1 when x is between, 0 and 5, and then in 3 when x is greater than or equal to 5, something like that. Then definitely you may want to use this method to do it. You can also use the indefinite integral, but they are a little bit, tricky, but you can use this one. This is much, much easier. So that's all I want to share on this one. I will stop it right here. The only thing that I would say is that, please review the worksheet or the homework number 2 on your Canvas. All right. I will see you in the next video of solving Bernoulli's differential equation. This is very similar, although this is section 2.5. This is very similar to what we just did, but I will do that in the next video.